Hello friends, this is Darwin Patel. Welcome to the lecture series of Mathematics-2. In this lecture, we will discuss about the application of Laplace transformation to ordinary differential equation. That means we will use the Laplace transformation to solve the ordinary linear differential equation. Before starting this topic, we have to understand the one property of the Laplace transformation, which is Laplace transform of derivative of ft. If Laplace transform of ft is phi of s or f bar s, then Laplace of derivative of ft, that means Laplace of f dash t, is equal to s into phi of s minus f of 0. That means when we want to find the Laplace transform of derivative of ft one time, we have to use this formula, and in this formula phi of s is a Laplace of ft, and we have to multiply phi of s with s, and f of 0 should be exist for function ft. If we want to find the Laplace transformation of derivative of ft two times, that means Laplace of f double dash t is given by formula s square phi of s minus s into f of 0 minus f dash 0. Here f of 0 and f dash 0 should be exist for function ft, and similarly we can find the Laplace of f triple dash t equal to s cube phi of s minus s square f of 0 minus s f dash 0 minus f double dash 0, where f of 0, f dash 0 and f double dash 0 should be exist. Sometime we will use these formulas to find the Laplace of cos square t, sin square t cos t sin t, etc. Here Laplace of cos square t is known for us, and it is obtained by the formula cos square t equal to 1 plus cos 2t by 2. Now we will use the Laplace of f dash t to find the Laplace of cos square t, which is 1 by 2, 1 upon s plus s in upon s square plus 4. First of all, ft equal to cos square t. So f dash t is minus sin 2t. Now we are taking the Laplace both sides. Then we get the Laplace of f dash t equal to minus Laplace of sin 2t. Now we will apply the Laplace of f dash t formula here. Then we get s phi of s minus f of 0 equal to minus Laplace of sin 2t. Now we know the Laplace of sin 2t. So we put the formula of Laplace of sin 2t, which is 2 upon s square plus 4. So our formula will be s phi of s minus f of 0 equal to minus 2 upon s square plus 4. Now ft is cos square t, so f of 0 is cos square 0, that is 1. So finally s into phi of s minus 1 equal to minus 2 upon s square plus 4. Now we will take the 1 on right hand side. So we have a s into phi of s equal to 1 minus 2 upon s square plus 4. Now we divide the last term by s. Then we get phi of s equal to 1 upon s minus 2 upon s into s square plus 4. After properly simplifying, we get the Laplace of cos square t equal to 1 by 2, 1 upon s plus s upon s square plus 4. So this is the second trick to find the Laplace transformation of cos square t using its derivative. Now we will go to the topic, the application of Laplace transformation to ordinary differential equation. Here we will discuss this topic for the second order non-homogeneous linear differential equation. Here a2y double dash plus a1y dash plus a0y equal to r of t be a second order non-homogeneous linear differential equation where a2, a1 and a0 are constants. Here Laplace of r of t is known for us. Let L inverse of phi of s equal to yt be a solution of our differential equation with respect to the condition y of 0 equal to k1 and y dash 0 equal to k2. Generally in the example, y0 and y dash 0 is already given. When they are not given, we can take the k1 and k2 as per our requirement. Now to solve this differential equation using the Laplace transformation, we first assume that yt equal to L inverse phi of s, that can be written as Laplace of yt is equal to phi of s. Now we take the Laplace both sides, then we get Laplace of y double dash a2y double dash plus a1y dash plus a0y equal to Laplace of rt. Here we already know the Laplace of rt. Now we separate the Laplace using the linear property of Laplace, we get the a2 Laplace of y double dash plus a1 Laplace of y dash plus a0 Laplace of y. As we know the Laplace of f double dash, Laplace of f dash, then we apply here. Here Laplace of y double dash formula is a2 into a square phi of s minus s y of 0 minus y dash 0. Here y of 0 and y dash 0 are known for us. Now we apply the Laplace of y dash formula, which is Laplace of y dash equal to s into phi of s minus y of 0, and Laplace of y is phi of s, we assumed it. So our final term will be a2 into s square phi of s minus s y of 0 minus y dash 0 plus a1 into s phi of s minus y of 0 plus a0 phi of s equal to Laplace of rt. Now in the next step, we will take the phi of s common, then we get a2 s square plus a1s plus a0 into phi of s. As we know that y of 0 is k1 and y dash 0 is k2. So finally we put this y of 0 value in this equation, and after simplifying we get minus a1 k1 minus s into a2 k1. Now we will put the value of y dash 0, then finally we get the minus a2 k2, and right hand side will be Laplace of rt. In the next step we make a phi of s as a subject, and then we get the phi of s equal to a2 k2 plus a1 k1 plus a2 k1s plus Laplace of rt upon a2 s square plus a1s plus a0. Now we will take the inverse Laplace both sides, then we get the L inverse of phi of s equal to y of t, which is our final solution in terms of t. So now we revise the step to solve the differential equation using the Laplace transformation. Here first we take the Laplace transformation both sides to the differential equation and apply the formula of Laplace of y dash, y double dash, y triple dash, etc. and then put the proper formula and simplify and make the phi of s as a subject, and then take the inverse Laplace of that particular function of s, and we get the particular solution of that differential equation. Now we will show the one example related to this topic. Here we will solve this differential equation using the Laplace transformation. Here our differential equation is y double dash plus 2y dash plus y equal to 4 e raised to minus 4t with respect to condition y of 0 equal to 0 and y dash 0 is equal to 1. Here we will use the Laplace transformation to solve this differential equation. Here we start with the Laplace, taking Laplace both sides, y double dash plus 2y dash plus y equal to Laplace of 4 e raised to minus t. Now Laplace of y of t equal to Laplace of y equal to phi of s. This is our first step. First of all, we assume the Laplace of yt be a solution. That implies L inverse of phi of s yt be a solution of our differential equation. Now we will separate the Laplace both sides, then Laplace of y double dash plus 2 Laplace of y dash plus Laplace of y equal to Laplace of 4 e raised to t. We have a formula of Laplace of y double dash, so we apply it. Here it is s square plus into phi of s minus s into y of 0, which is known for us, minus y dash 0, it is also given in the question, and plus 2 into Laplace of y dash. So we are applying the Laplace of y dash formula here. So it is s into phi of s minus y of 0, which is given in the question, and Laplace of y is equal to phi of s. So plus phi of s 4 into 1 upon s plus 1, which is our right hand side Laplace. Now we take the phi of s together from all three terms. Here we have a 3 phi of s, then take the common. So we have a s square plus 2s plus 1 into phi of s. Now our y of 0 is given and y of 0 is 0. So we apply at two places s into y of 0 and minus 2 into 0. Therefore, minus s into 0 and 2 into 0. Now y dash 0 is also known, it is 1. So we apply at y dash 0 in the first term. Then we get minus 1 equal to right hand side is as it is 4 upon s plus 1. Now first term is perfect square of s plus 1, so it is s plus 1 whole square into phi of s. These two terms are 0, so we don't consider, and right hand side will be 4 upon s plus 1 plus 1 go to the right hand side, so we have a right hand side is 4 upon s plus 1 plus 1. Therefore, phi of s equal to 4 upon s plus 1 whole cube plus 1 upon s plus 1 whole square. Now we will take the inverse Laplace both sides, then we get inverse Laplace of phi of s equal to inverse Laplace of 4 into inverse Laplace of 1 upon s plus 1 whole cube plus L inverse of 1 upon s plus 1 the whole square. Here in the both term we have a s plus 1, so it is a first shifting property. First of all, we convert into the s term by multiplying with e raised to minus t into 4 upon s square s cube plus 1 upon s square, and take the inverse Laplace, which is our first shifting property. Here s is replaced by s plus 1, so we are applying the first shifting property. Now we know the inverse Laplace of 4 upon s cube, which is 4 into t square upon gamma 3, plus we know the Laplace inverse of 1 upon s square, which is t upon gamma 2. Now we will put the gamma 3 equal to 2 factorial. So we have a e raised to minus t into 4 t square by 2 factorial, and gamma 2 is 1 factorial. So t upon 1 factorial, and now we cancel with 2. Then finally y of t, which is our final answer, is e raised to minus t into 2t square plus t. So this is the method to find the particular solution of our given differential equation with respect to given condition using the Laplace transformation. Here yt equal to e raised to minus t into 2t square plus t be a particular solution of our differential equation y double dash plus 2y dash plus y equal to 4 into e raised to minus t according to the condition y of 0 equal to 0 and y dash 0 equal to 1. Here this method is only applicable when the right hand side function's Laplace is exist. That means it follows the existence conditions of the Laplace transformation. Otherwise we can't apply this Laplace transformation to differential equation. Thank you very much.